It's a great pleasure being here. Thank you, the organizers, for having invited me to this wonderful conference. I really enjoy being here, being at the other beautiful end of my own country. Okay, I would also like to acknowledge my main collaborators in this research, Sarah van de Geer and Nikolai Meinshausen. They both made very important contributions together with me as well. Okay, so it's about high-dimensional data. Here's the first example, which I would like to show you a bit, and then towards the end of the talk I'll come back to the example again. It's about behavioral economics and genetics. This is a joint project with Ernst Fehr from University of Zurich. The problem is as follows. We have about 1,500 people in a study. We measure genetic information for each of the probands. So we have that in terms of SNPs. If you don't know what SNPs are, I'm not going into details about this, but you measure a lot of biomarkers per person. So we have about 1 million biomarkers for every person, and we have 79 response variables. They measure kind of behavioral tasks, behavioral activity, behavioral indices of each of this person. So think about this as risk aversion, degree of altruism, and so on and so forth. So this is kind of quite a modern, apparently modern application in behavioral economics. And the only goal here is to find significant associations, potential associations between genetic biomarkers and behavioral profile. Okay. So let's go into that problem. So it's high dimensional because P, the number of biomarkers, is much, much larger than sample size, and actually making significant statements is not entirely trivial in that sort of framework. So I think it's fair to say that a lot of progress has been achieved over the last 8-10 years in many areas of high-dimensional inference, high-dimensional prediction, high-dimensional parameter estimation, variable feature selection. But actually there is very little work which has been done on assigning measures of uncertainties, p-values, confidence intervals. Some sort of very classical concept has not been addressed very much in the past. I'm talking here about p-values and confidence intervals in the frequentist setting. I'm not talking about the Bayesian setting. That would be an alternative route to go and quantify uncertainty. Okay, so I want to do uncertainty quantification. This is the core of statistics. I think statistics is in a unique position to make uncertainty quantification, and this is a very hot topic now. There's a new journal which has been launched by SIAM and ASA exactly with that title, uncertainty quantification. So my goal is a bit more specific here for this presentation. What I want to show you is how can we assign p-values for a high-dimensional linear model. I'm going with the simplest model, a high-dimensional linear model, and I want to assign p-values or confidence intervals. Once we understand it with this model, you can generalize to other models, and that's not so difficult. I want to move that a bit away. Okay. And I should also say this is something which is much beyond, say, marginal correlations. This is what many people do. If you have very high dimensional problems, you can just look at marginal correlation of, say, a y and one variable x, regardless how many, or almost regardless how many dimensions you have. But here we're trying to do this in a linear model which is much different than marginal correlation. Okay, so here is another example. It's also from my area of interdisciplinary research, from computational biology. It's much smaller scale, but I think it's kind of useful for illustration purposes. The example is about so-called motif regression, and so the goal is to find binding sites on DNA sequences. So we have DNA sequence, we think of this as a linear sequence. It has positions with the base pairs A, C, G, and T, and then there are small words in this sequence, like a word CGTGC, 5, 10, or 15 base pairs long, and these are positions where a particular protein or a particular transcription factor binds or attaches to the DNA. So the transcription factor, the protein we're interested in, is called HIF1 alpha. Alpha is kind of a very mathematical name, so biologists also use the alpha. So HIF1 alpha is the transcription factor of interest, and it's associated to cancer disease. So this is kind of the protein I'm interested in, and I want to know where exactly on the DNA this HIF1 alpha binds or attaches to the DNA. Okay. So the kind of measurements which we had a couple of years ago, now that we have new technology, you can do this differently. But again, this is more an example for illustration. The kind of measurements which we had a while ago are univariate response variables y. So y measures the binding intensity of this HIF1 alpha on rough, large segments of the DNA sequence. So like a segment of 500 or 800 base pairs long. So in such a large segment, I have pretty good information how well HIF1 alpha binds to this large region. But I want to go to the small resolution. I want to go onto short words, like 5, 10 letters long. And in order to do that, there is kind of a trick which has been used many times, at least a couple of years ago. So the trick is you create many candidate words. You create small words. You use some sort of computational biology algorithm, and you create these words of 5, 10, or 15 letters long. Like one word could be CGTGC. And in our example, we created actually 195 such words. Okay, now what we can also measure is how often does such a short word occur in your large DNA segment I. So you can measure the abundance of your candidate word in your DNA region I. And so this is my Xij. Xij is the abundance or the relative frequency of my candidate word J in segment I. Okay, so that's the kind of data. It's some sort of like regression type data. I have a y, I have x's, and now the question is how can we relate the binding intensity y and the abundance of short candidate motifs? And a bit surprisingly, a linear model, this is not our idea, but a linear model works surprisingly well to explain your rough binding intensity, the binding intensity on the large DNA segment. You can explain that fairly well with your abundance scores with a linear model. Okay, this idea has been put forward by Jun Liu and colleagues a while ago at Harvard, and they were quite successful by saying just use a linear model to combine these two sources of information. Now this is an example which is slightly high dimensional. We have 143 DNA segments and we have 195 candidate words, so we have a bit more variables than sample size, so it's a bit more high dimensional as usual. The other thing here which is interesting in this problem, I think the goal from a scientific point of view is variable or feature selection only. Nobody is ever interested in predicting this y. You can just measure this y. You don't want to predict that. You only want to know which of these candidate words or their abundance scores are important for explaining your y. And you measure importance in terms of regression coefficient beta. So whenever I write a beta 0, I mean this is the true underlying regression coefficient of the model. Okay, so I want to do variable selection, and once I have done this, I would say, okay, here are my relevant motifs, and hopefully they have some sort of biological meaning. So let's do that. So I think in statistics, but also now in engineering, L1 penalized regression is extremely popular, so you can try to do that with the lasso, so you minimize residual sum of squares, and you regularize or penalize with the L1 norm. There's this tuning parameter lambda, and there are these well-known facts that, I mean, this is a convex optimization problem, so this is easy, and it's a sparse estimator, so some of the coefficients are exactly 0. Okay, so that's just written here. So we use the lasso for this problem, and we also should say a brief word, how do we now measure importance of a variable, or how do we do feature selection? And this is what most people do now, at least in a preliminary stage. So the first task you want to do is to infer the active set here. So S0 are the variables, these corresponding regression coefficients different from 0. So this is the support of my parameter vector beta 0. And I simply estimate the support S0 by S hat lambda, and S hat lambda is just when you use the lasso or L1 penalized regression, these are the variables with corresponding regression coefficients different from 0. So this is super simple because you have a sparse estimator, you immediately have some sort of a sparse estimated set. It's convex optimization only, that's great. You can do this on much larger scales, of course. And it's also in a way convenient because you don't have to go through this hassle of significance testing. You just get out these estimated variables and you claim, okay, here are my features which are important. It's very popular nowadays. I think in bioinformatics, in computational biology, and probably in many other areas, this is some sort of a workhorse. In a preliminary stage, you run L1 penalized regression, and you do some sort of preliminary feature selection. Okay, so for my motive regression example, I remind you again, n is 143, p is a bit higher than n, 195. If we do this, if I choose my lambda with cross-validation, that's somehow the standard thing to do, the lasso L1 penalized regression selects 26 variables. Okay? And you can then compute the corresponding R squared. It's about 50%, and this is very good, this is very high in this sort of application. So the preliminary conclusion would be, okay, there are 26 interesting candidate motifs, so 26 relevant biological features, and that's simply not true. So biologists would say there is maybe 1, 2, at most 3 different binding sites for this HIF1 alpha, not 26. So these are too many features you select. Okay. So the question is, do we trust this selection algorithm? It's very simple, it's very convenient, and how stable in a way are the findings? How stable are these 26 variables? So let's look a bit what the result actually is. On the x-axis, you see the 195 variables, the indices of these variables. On the y-axis, the estimated regression coefficients. So one variable, I don't know, about 60, has a fairly large regression coefficient. 25 others are non-zero, they're not so large, and the remaining stuff is 0. Okay, these are my 26 selected variables. And it's kind of clear if you look at this picture, if you need to kind of screen out or sort out which one is the most important one, everybody would say, okay, this is the largest, it's the most important. You could just sort or rank according to the magnitude. But that's not taking uncertainty into account. If you want to take uncertainty into account, you have to go one step further. And what I would like to know is somehow, what is a p-value for, say, the jth hypothesis? The jth hypothesis is the beta j is equal to 0. And the alternative, it's non-zero. So this is kind of like the classical thing you get from a statistical software. You get a column of p-values. But because it's high dimensional, it's not so easy to do that. But that's what I want to have. I want to have these p-values. Okay, so let's go a bit into that. I want to say some words and explain a bit some of the conditions we use nowadays in high-dimensional linear models for also what kind of things are used in statistical theory. I'm just very brief on that, but I want to make clear what these assumptions, what kind of role they play. So here is my high-dimensional linear model. Everything is standard except that p might be much, much larger than sample size. My X matrix here is, for simplicity, it's assumed to be fixed design, but it can generalize to random design. That's not a big issue. Now, the first thing, of course, it's, I think, clear to this audience, but I nevertheless pointed out there is a problem of identifiability. If p is larger than n, x beta 0 can always be written as x theta for any theta which is equal to beta 0 plus an element xi, and xi is in the null space of x. The null space is not empty because p is larger than n. So obviously, if you want to say something about your beta 0 and also p-values about the components of beta 0, you need to make some sort of identifiability assumption, otherwise you cannot say anything. Okay? And so that's the first main assumption you need if you're interested in the beta vector. Okay? Assumption 1 is conditions on the design, on the x, and what most people, at least in the statistical literature now do, they formulate these conditions in terms of so-called restricted eigenvalues. And I go very briefly into that. So the matrix of interest is sigma hat. This is x transposed x normalized by n. This is something like the empirical covariance matrix of x. Okay? So obviously sigma hat is singular if p is larger than n. But nevertheless, we can look, say, at the minimal eigenvalue of this symmetric matrix, denoted by lambda squared min, and the minimal eigenvalue always fulfills this inequality for all coefficients beta. You can relate the 2 norms squared with the quadratic form here if you kind of divide by the minimal eigenvalue, right? So the minimal eigenvalue is 0 if p is larger than n, but the inequality is still correct. You just have infinity on the right-hand side. Okay, this is not informative. Now you have to do something more informative, and what people do now is, okay, they say, we ask for a restriction of this inequality. And the restriction is a bit complicated, but it goes as follows. So we look at the so-called restricted, and I do the L1 eigenvalue. So I relate, instead of the 2 norms squared, I take the 1 norm squared. And it's a bit a different inequality here. So what I do is I take my regression vector beta. I have the indices in the active set here, S0. So these are the indices of beta in the active set. 1 norm squared, I relate it to a quadratic form here, beta transpose sigma hat beta. I normalize with the cardinality of the active set, and I divide by this restricted eigenvalue. So phi 0 squared is the restricted L1 eigenvalue, or it's also denoted or called sometimes the compatibility condition. Now you require that this inequality here, which is of course less informative than this one, but you require that this doesn't need to hold for all beta. You only require this to hold for beta satisfying a cone condition. Okay, so here's a cone condition, so only for the betas which satisfy this. So these are the indices in the complement of S0. Here are the indices in S0 in the active set, and the factor 3 is not important. It can be replaced by another factor. So this is the restricted L1 eigenvalue of your matrix, and that all of a sudden becomes informative if P is much larger than N. So many people have worked in this field, and I try to give a small overview here without going into the details. So here you see various conditions, and I think it's quite useful to see a bit what's going on. On the left-hand side you see RIP, the restricted isometry property, Candice and tau and many others, and that's a very strong condition. So if you look at this diagram, there is a tendency you kind of go more to the right than to the right and to the right, right? So everything is weaker on the right-hand side, and on the right-hand side you have the restricted eigenvalue conditions. So restricted eigenvalue conditions are strictly weaker than restricted isometry property, yet they are still good enough for the main statistical tasks which you want to do, namely parameter estimation and, say, variable screening. Okay, so my point is restricted eigenvalues are weaker than restricted isometry property, but maybe there are even weaker versions nowadays which kind of generalize a bit. Okay, so what can we say with L1 penalized regression with the lasso if we make such a restricted eigenvalue condition? So if the restricted L1 eigenvalue is, say, bounded away from 0, and I'll come back to that, how restrictive that assumption is, then you get a reasonable result for prediction. I'm not that interested in prediction. I'm interested in estimating my beta 0, my parameter vector. And for example, I have a result on the 1 norm. Beta hat with the lasso minus beta 0 1 norm is bounded by this quantity. S0 is the sparsity, sometimes it's denoted, I think, by K in your community. So S0 is the sparsity, the number of non-zero coefficients in the model. And I have square root log P over N, and of course my regularization parameter needs to be chosen appropriately, and the right scaling here is also square root log P over N. Okay, so what do we see from this? You see kind of a bound, but you also see things become identifiable, right? Now beta 0 is identifiable if this goes to 0. And this is even a constructive proof why it's identifiable. You can get it with the lasso. So the lasso gives you the identifiable parameter. So the point is, if it is sparse, and sparse means S0 needs to be of smaller order than square root N over log P, so that allows for quite high dimensional problems, then the parameter is identifiable under the L1 eigenvalue condition. Okay? So this is a way what I want. I want to have identifiability in my parameter, and that's satisfied with an L1 eigenvalue condition. The question is a bit, does this condition make sense? Does it hold in practice? And I think an honest answer is, I'm not so sure in real practice, but I think here is a nice mathematical result which gives at least some indication when this L1 eigenvalue condition holds. You can actually not check it easily because you don't know your true underlying active set, so it's very hard to check that condition. Okay, so let's assume that my design matrix is sampled as IID rows, right? I have my n, these are my rows, and these rows, the columns can be correlated, of course. Think about, I have x1 to xn IID p-dimensional Gaussian with mean 0, that's not important, and a covariance matrix sigma. So sigma doesn't need to be the identity, it can be something much, much more general. And what I require here is the compatibility constant, or this L1 eigenvalue for sigma. That's a different thing, that's my population sigma. So I require that this, say, is bounded away from 0. For example, if the eigenvalue of sigma is bounded away from 0, the restricted eigenvalue is bounded away from 0 as well. So for example, take sigma as a Toeplitz matrix, take sigma as an equicorrelation matrix, as a block diagonal matrix, then the L1 eigenvalue is always bounded away from 0 for sigma. So there is no sample size involved, this is only a p-dimensional matrix. Okay, then you make moment conditions for x. For example, it's a Gaussian or a sub-Gaussian x. And then you require sparsity. You say S0 has to be of lower order. Now I can even relax the square root. Lower order of n over log p. And then the result says the L1 eigenvalue of my realized x, this is my sigma hat, right? The L1 eigenvalue of my sigma hat can be bounded from below by the L1 eigenvalue of the sigma. So if this is bounded away from 0, this is bounded away from 0 as well. So the message is actually this L1 restricted eigenvalue does hold for sparse problems if the for sparse problems if the sigma behaves sufficiently nice. Okay? So that's the message. So that gives some sort of idea. It's not such an unreasonable assumption. So with high probability, actually, this behaves nicely. Okay, so that's my main first assumption, which you typically require. The second assumption, which you often do, but not always, is a beta-min condition. The beta-min condition, so here I have a rate result, again, under the L1 restricted eigenvalue condition. And now there's an immediate implication of that. If the non-zero elements of beta are sufficiently large, so I look at my beta 0 vector, I take all j's in the active set. If the non-zero betas are sufficiently large, and sufficiently large means larger than this convergence rate, then there's a one-line proof that then it must be that S hat, the variable selected, say, by lasso, they must contain the true active set. Okay, and that's a very beautiful result in a way, and very interesting for practice. This is called variable screening or dimension reduction. I can do dimension reduction. Think about, I have the 10,000 variables to start with. The lasso selects, say, 60 of them, and then I would know, okay, the true active set must be contained among the 60 variables selected by the lasso. Okay. So we will not miss a true variable, and we do dimension reduction in the original variable. It's not dimension reduction like PCA or something like that. So you do dimension reduction in your original variables. Okay, so let's go into that. So this is my motive regression example, the picture again. And if you believe this, if you think assumption 1 and 2 hold, then this is true. Then this would say, okay, my true biologically relevant motifs must be contained among the 26 selected variables from the lasso. Okay, but you don't know which one. You would say, okay, this is the best, maybe this is the second, but that's not so clear. And again, p-values would be useful. So now I want to go into quantify the uncertainty here. Okay, so p-values in a high-dimensional linear model. Here's again my linear model, and my goal is very classical, at least for me as a statistician. I have a jth null hypothesis that the jth coefficient beta j0 is 0 versus the alternative that it is non-zero. Or you can also look at the group hypothesis. Say you have a group of genes and you say all genes in that group have regression coefficients equal to 0 versus the alternative, which is the logical complement. Okay, so why is this problem so difficult? The background is as follows. if somebody could handle, say, the distribution, or at least the asymptotic distribution of the lasso, of L1 penalized regression, at least under the null hypothesis, then I'm in business. This is how you construct a statistical test. You study the distribution of your estimator under the null, and if you have it, you know how to construct a confidence interval and p-values. Okay? The problem is this is very difficult in high dimensions. In low dimensions, this can be worked out, and the difficulty comes into play because the lasso and any sparse estimator puts mass at 0, so positive mass at 0. This is surely not a Gaussian limit, because a Gaussian limit cannot have mass at 0, and it's very difficult. Nobody knows the answer in the real high-dimensional regime what the distribution is of a sparse estimator. And that also means the standard theory in statistics, there's a huge literature on bootstrapping, on subsampling, it cannot be used, because you don't know how the scaling is, what the distributional limit is of a sparse estimator. Okay, so you have to do something else, and I present two approaches what you can do, and both have their points. The first one is based on somehow maybe a very rough idea. Just do some sample splitting, and it's very easy to use, but it might be a bit suboptimal. But I'll try to explain here the concept. So the idea is you have your data set, you split it in two halves. You can also do a third, two-thirds, but let's just do two halves. And on the first half of your data, you select variables. So this is it. I select variables on the first half of my sample. This is my S hat, for example, using the lasso. And then you go with these selected variables to the second half. You only have now few variables left, maybe only 26, like in my example. And then I apply classical theory on the second half of the sample. I just stick it into my ordinary linear model software package, and it will spit out p-values. And I have to be a bit careful, so if the variable j has been selected in the first half, I take the p-value just from the classical t-test. And if it has not been selected in the first half, it's probably not a relevant variable, then you say, okay, let's put a p-value which is high, so it's not significant, so put it to 1. Okay. So why are we doing this sample splitting? If you wouldn't do it, it would be over-optimistic. This is called post-model selection inference. You're not allowed to first select the variables on the full sample and then use again the full sample to assign the uncertainty measure. That's over-optimistic. That's wrong. So that's why you need to split the sample. Okay, so you have these p-values like this, and then you do multiple testing correction. I'm interested in testing many of these hypotheses, so obviously I should adjust for multiplicity of the test. The easiest one is Bonferroni. You just multiply the p-value by the number of tests you're doing. Now, interestingly here, you only need to multiply your p-values by the number of variables you have selected in the first half. That's a great advantage. It's mathematically easy to prove that this suffices. And then if you have these corrected p-values, they're fine. So they're fine against multiple testing. So if they're below, say, 0.05, the variable is significant. If it's above, it's not significant. Okay. So these kind of p-values, they lead to at least conservative family-wise error control. And family-wise error control means the probability for no false positive selection is bounded by your alpha. Alpha is typically 5%. So this idea has been put forward by Wasserman and Roeder. This is very nice, very simple, very pragmatic. And it works beautifully in simulations. And then if you look at it actually on a real data example, it's terrible. And why is it terrible? It's what we call a p-value lottery. So this is my motive regression example again. And I look at just one particular variable, say number 7. That's a nice number. And I compute the p-value for my 7th variable based on sample splitting. I get a value like 0.12. Now I do another sample splitting, randomly split the sample. I get another p-value of maybe 0.89, and it's terrible. I do it, I think, 500 times, and you see the different p-values which arise just due to the fact how you have splitted the sample. And that's terrible, right? The method should not depend on how you split the sample. I mean, asymptotically everything works, but in practice it's huge failure. And we call it a p-value lottery. It's really a lottery how you split the sample. That gives you the result. So this is not good. Now obviously you can repair this. You can of course do this sample splitting many times and then aggregate over these p-values. So you can look at this picture and the question would be, how can I aggregate these p-values to a single value? And most people might take the mean, but that's not right. You should not take the mean. And that's a bit an issue, and I'm not going too deep into that. But I want to tell you how this can be done just on the surface. So you run this sample splitting procedure capital B times, say 100 times, and then I have to skip this due to time constraint. You do a non-trivial p-value aggregation. There is some sort of a nice scheme how you can come up with a p-value such that it's a valid p-value. It leads to error control. Okay, so here's the final result of such kind of a procedure. The assumption is, say, a Gaussian linear model, fixed design, and there are two assumptions, and I think they're kind of important to be pointed out. The first assumption is my screening property. S hat must contain the true active set with high probability, or probability tending to 1 in the limit. So we discussed that earlier. This requires L1 restricted eigenvalue, and it requires the beta min assumption. Okay. The second assumption is a weak one. S hat cardinality needs to be less than sample size. You only work on sample size in half. It needs to be less than sample size in half. The lasso L1 regularized regression fulfills that for free. So this is no condition for the lasso. And then you're fine. So here's a procedure which gives me family-wise error control. That means probability for no false positives can be bounded by alpha. It can also be done for, say, false discovery rate control and so on and so forth. Okay, this is based on multi-sample splitting. This is the motive regression example. P is 195, N is 143. This guy here, the red one, indeed, it is significant. It has a p-value of 0.006. Say if my significance level is 5%, it's below, so it's a significant finding. And there's this blue guy here, which has a p-value clearly larger than 0.05. I think it was 0.11. And so the blue one is an interesting one because it's a biologically known relevant motif. So here is a true variable which biologists know. And it's not significant, slightly not significant. Here is another one which they don't know it's significant. We haven't done any follow-up experiments on that, but it's kind of a reasonable result. This procedure, at the end of the day, selects one significant binding site, and that's kind of in the right order of magnitude. It should not be 5 or 7. That's too much for biology. 1, 2, or 3 is fine. Okay. Simulations, let's skip that. Let's discuss this. This multi-sample splitting method, it has this one major assumption, the screening property. I don't need it, it's not necessary, but so far as I explained it, it's this assumption of the screening property S hat must contain the true active set S0, at least in the limit. And for that here, you necessarily need the beta min condition saying that the non-zero betas are sufficiently large. And now comes some sort of philosophy or aesthetic reasons why this is not good. If I want to test significance of a variable, I somehow want to test whether a coefficient is large or not. And I don't want to make an assumption on that coefficient. So this is a method which works if I'm willing to make an assumption that the non-zero betas are sufficiently large. But that's in a way the essence of the question. I want to find out by my p-values or significance statements whether a coefficient is large or not. So that's the reason why I don't like somehow this condition. It can be relaxed a bit. So it's not necessary that you have this, but you necessarily need what we call zonal assumptions. And just look at this picture. A zonal assumption means many of your true betas are 0. You might have some betas which are small and non-zero. They would not fulfill the beta min condition. They're small. And then you have large betas which are detectable. And a zonal assumption requires that there must be a sufficiently large gap between the small non-zero coefficients and the large one, the detectable ones. And this is necessary. And again, it's not so nice. It's the essence of the question to find out whether there is a gap or not. Now we have a method which says, okay, if you assume there is a gap, then we're fine. Okay. The method necessarily requires identifiability conditions on the design, but that's unavoidable. This is identifiability, and that's more a practical issue. The method is easy to apply, it's very generic, and we have an R package, it's called HDI, high dimensional inference. It spits out these p-values. Okay, so now comes something else. How can we avoid this beta min condition? And actually you can. And the idea is based on something completely different, and I think it's kind of interesting, and I think I'm quite excited about this as well. We can do some sort of low-dimensional projections and bias correction. I want to point out that Zhang and Zhang, so this is Zhonghui Zhang at Rutgers and his daughter, they proposed the same thing around the same time, so we're kind of doing independent work on that. And so let's understand a bit what I want to do. The motivation is this. Okay, if you're in a classical situation, you can get your jth coefficient in ordinary least squares by a very simple trick. You can project the y onto the residuals when you do a regression of xj versus all other variables. So you do xj, you regress it on all xk, k different than j, you have the residuals, and you project y onto the residuals, and that's your jth component of your ordinary least squares estimator. Okay, now let's try to generalize this super simple idea into high dimensions, and the problem is, of course, the projection is not working onto these residuals because they're not well defined, they're zero. If p is larger than n, you overfit and your residuals are zero. So the idea is you use regularized residuals, and while this is a sparsity conference, let's try to use the lasso to do this. So you run the lasso of xj versus all other xk's, and you denote the residuals by zj. Okay? That's very easy to do. Xj variable, do the lasso against all others, get the residuals, and now kind of project y onto these zj's. Let's do this. Okay, I project. It's not quite a projection, but almost. So I look at zj transposed y. This is linear in y. This is super simple. You plug in the model formula. It's linear, so it's very simple to do. So you have this term. Then you have the term with the k is different from j plus the error term. Epsilon is a Gaussian, say, error term, so I have zj transposed epsilon. Hence, if you divide or normalize by zj transposed xj, so here is my linear estimator. I get what I want. I want my beta j0, my regression coefficient. I have an additional term, and this is what I call the bias term. It doesn't exist in least squares because they're all orthogonal. They're not orthogonal anymore because I do a regularized projection. So I have a bias term and a noise component. And now you only need to estimate that bias term. So what can you do? You say, okay, I estimate the bias term, say, with the lasso, and then you subtract it. So my new estimator is this linear guy in y minus a lasso estimated bias term. This is a new estimator. Call it bj hat. This is an estimator for beta j0. This is a sparsity conference, but b hat is not sparse. None of them is zero. They're all non-zero. You say, okay, this is bad. I say, this is good. This is very crucial to obtain a Gaussian limit. You would not get a Gaussian limit with a sparse estimator. And this is even optimal for the sort of stuff I want to do. It's not good for prediction. We know for prediction we need sparse estimators. But for my task, this is optimal. Okay, so why can this work? And the main answer is the target is different. My target is a very low-dimensional component beta j0. I have my huge high-dimensional beta vector, and I'm just interested in the jth component. It's a very low-dimensional target. Then there are all the other coefficients. This is typically denoted in statistics by eta, and eta is called a nuisance parameter. I'm not interested in these guys. Okay? So this is nuisance parameter, and this is called a semi-parametric model. A semi-parametric model has a very low dimensional target of interest and a very high dimensional nuisance parameter. This is exactly this situation, and I estimate my high dimensional nuisance parameter with the lasso. That was my bias correction. Okay, so there's actually a general principle behind this. So this is a bias correction with the lasso. There's a very general principle behind this, and I'm just outlining this very quickly. You can get to that estimator by inverting the KKT conditions. So you write down the Karush-Kuhn-Tucker conditions for the lasso, and then you need a regularized inverse of the sigma hat. And through that inversion, you can construct an estimator. I know this is way too fast, but somehow I have this B hat, which comes from inverting the KKT conditions. And at the end of the day, I get exactly the same estimator like this bias correction. Okay. So my point is, this is going with a very different idea. It's inverting the KKT conditions, and so that means I can apply this idea not only for linear models, I can do it for generalized linear models, for graphical models, and so on and so forth. I claim I can do this now for any kind of convex optimization procedure where I have the KKT condition, and I need to properly invert that. Okay. So why does this work? I want to go very briefly a bit into technicalities. So the only problem I have is my bias correction. So if you look at this here, this estimator is fine. It gets exactly what I want up to noise term and this bias. So I correct it with the bias, I use the lasso, and the only error I do is potentially in the estimation of bias. That's the error which I have to deal with. Okay. And so let's analyze this. So this is the estimated bias minus the true bias. This is exactly of this form. And it involves this stuff here, Cj transpose xk divided by this. Call it pjk. These are just certain values. Times the lasso estimated beta minus the true beta 0. Now you bound this quantity. This is a trivial bound, but it's quite sharp. You bound this by max pjk times, and now this is our old friend, the L1 norm of the lasso. Okay? So this is, we know how to do this, how to deal with that. Now we have to talk a bit about this pjk. You can say, okay, pjk, you see it from your data. It's a value, it's a number, and it's typically small. That's not so satisfactory from a theory point of view, but there's a very simple bound for the max pjk as well. You invoke KKT condition, it's kind of near orthogonality of the lasso, and that means max pjk is bounded by this lambda x divided by this. And what is lambda x? Lambda x is the regularization parameter when I use the lasso of xj versus all other variables. Okay, you have it under control. Up to this guy here, and the right scaling for lambda x, you should choose it as square root log p over n. So roughly, if you scale up the error in the bias, you have this bound here, square root n, then this is our old friend. This is the lambda x, is square root log p over n. You pull it together, you have this, and so this goes to 0, and again this fits to the conference if the signal is sparse. If the number of non-zero elements is of smaller order than square root n over log p, you're fine. Okay, so here's the theorem. And the nice thing, I think, if you have exposure to statistics, that's the usual type of theorem you see in classical settings. It's almost, you have an estimator, you have square root n convergence rate, and you have a Gaussian limit. And we have it also. It's a non-sparse estimator, I agree, but it's for my jth component. So I have this estimator, I subtract the true parameter, I scale it with square root n, I have the Gaussian limit, and this omega matrix, jth element, I know it. It's fixed design, I can compute what it is. I need to estimate sigma squared epsilon, but I can do that. And the interesting thing is, one can easily prove that omega actually converges to sigma inverse under some conditions, and that's the optimal you can do. So this is an optimal procedure to get a p-value for beta j0. Okay, so what are the assumptions for this optimality? The assumptions are here as follows. I assume my design is generated by IID sampling of the rows, and it has a covariance x, sigma, and I assume sigma has eigenvalues bounded away from 0. A Toeplitz matrix, equicorrelation matrix, and so on, that's fine. I assume sparsity of y versus x, so that's the kind of quite usual rate. S0 needs to be of small order than square root n over log p. That's okay as well. And then I need something else, and that's maybe not so okay. I need also sparsity when I do the regression of xj on all others. And that essentially means I assume sigma inverse is sparse as well. And that's not so clear in many applications, and I have a bit of question mark around this assumption. Okay. If you are willing to make this assumption, you really find you have a very cool solution to this problem. It's the optimal solution. I think I should go a bit faster through that. There's uniform convergence. You can do simultaneous inference over many components. You can test now groups. That's all good. Let's go to the motive regression example. P is 195, N is 143, and I get the same answer with like multi-sample splitting, and that's nice from a scientific interdisciplinary point of view. Regardless what kind of method you take, you get the same scientific conclusion. This guy is significant, and this one, the true motif, is not significant. Okay, so now let's push a bit further and see how this works and what we can do. The recap about this optimality is, okay, sigma has to have bounded eigenvalues bounded away from 0. Sparsity for regression, I found that as well, that's okay. And sigma inverse is sparse. And I'm not so okay with this assumption. Now you can actually drop this assumption. And that's kind of neat. So that was actually my older proposal. You can do, for example, ridge regression. You do xj and run a ridge regression against all other xk's and get the residuals and do the same stuff again. And then I don't need an assumption on sigma inverse, but I don't get an optimality result either. Okay? So I have one assumption less on a design, but I don't have optimality anymore. Okay, you can also run a convex program for the construction somehow of the best residuals. You don't need to use ridge regression or lasso for constructing these residuals. You can run a convex program for that. That has been independently somehow developed by a master student of mine and by Chavanmar and Montanari, and you can run this convex program and try to get rid of sigma inverse. So here is the program, and actually Chavanmar and Montanari, they prove something about that, but again, optimality is lost. That's the price you pay. So let's discuss this a bit. So this is this other way how you can get to p-values, low-dimensional relaxed projection. It doesn't need this beta-min assumption. This is really nice. So I really kind of don't like this beta-min assumption because it's the essence of the question, so I don't need that. The method necessarily requires identifiability conditions on the design, but that any method probably will require that. And we have optimal detection, optimal power if we're making the assumption that the design is sampled from a sigma where sigma inverse is sparse. Then you're in the optimality regime. Practically also it will be in the same R package, so you have a choice. You can take this method or that, or you can try both and see what happens. Okay, so does this all work? And to be honest, I think this has potential, and all of these methods have also difficulties. The difficulties in general are still ill-posedness of design, and a difficulty might also be maybe my true signal is not sparse, and then I have a problem. Okay. Now for the projection estimators, with this bias correction, I'm going a bit faster here, just drop this, but go into this red stuff. There is an interesting observation and some sort of theoretical explanation that if you go to the high signal-to-noise ratio regime, okay, if the signal is strong, we think this is great, right? It's of course great for detection. I will detect my variables, but it's not good for error control. So if I want to guide against or be guarded against type 1 error, then high signal-to-noise ratio can be a problem. And that's a bit peculiar, so there are some difficulties here as well. And so we actually went a bit into a larger simulation exercise, and it's not quite finished yet. So we want to compare power and reliability of error control with these methods. We don't make it that high dimensional. P is 500, N is 100. We have 15 active variables, sparsity is 15, and we generate a couple of designs where the design matrix comes from a Gaussian with covariance matrix sigma. And we have different scenarios, so each dot here is a different scenario, a different beta vector, a different constellation of the active variables, and so on. Okay, the first example is a hard one. This is equicorrelation. Every variable is correlated with every other variable with 0.8. This is quite high correlation, but let's see what happens. So sigma inverse is not sparse at all, it's terrible. And what you see here are plots. This is the multi-sample splitting method. So here on the x-axis is family-wise error control, or family-wise error rate. I'm aiming for 0.05. On the y-axis is power. Okay? And power is average power. So the multi-sample splitting is reliable but has no power. This is a very hard example. Then this is this rich projection, which in theory doesn't need that sigma inverse is sparse. It's not reliable anymore for error control. It has not good power either. And this lasso optimal procedure is terrible. I mean, the error control is not here at all. And the assumption is violated. Sigma inverse is not sparse. So it's terrible. Okay, then you can go to more sparse sigma inverse. As soon as you go to more sparse sigma inverse, so this is this lasso optimal method. There's still one guy where there is no error control, otherwise it behaves quite nicely, has a bit more power than the others. Now this is a Toeplitz design. Sigma inverse is very sparse, and this optimal method indeed is best. Here you're fine as well, but you lose power with multi-sample splitting. I think more interesting is really go to real data. So do some sort of pseudo-real data. You take an X from real data, say a gene expression data set, take 500 variables, and then you create artificial beta vectors, Gaussian error terms, and then see what happens. So my design is now real data design. And this optimal method is pretty terrible in error control. Probably sigma inverse is not sparse. I don't know, it's real data. But it doesn't behave very well. They're reliable in terms of error control, but they have less power. Here's another real data constellation. Here the optimal method is actually fine, and the multi-sample splitting, this is the only case where we don't have reliable error control. Okay, what is somehow a conclusion of that? Overall, so far, what we find, and we try quite hard, I don't have a bias whether I want to have this method to win or the other. I'm just open which one is good or not. The multi-sample splitting is most reliable in terms of error control, so far, what we see. And the price is in terms of power. And here are two famous people, Leo Brime and Brad Ephron. Both of them have repeatedly propagated that the random resampling is a good thing, it makes things stable. And so maybe our results are a bit in line with what they have propagated many years before. I think I'm running out of time, so I'll... Right, so well, okay, so here's this example I started with, this behavioral economics example. I remind you, 1,500 people in the study, 79 behavioral experiments, whether you are risk averse, have a high degree to altruism, and so on and so forth. And we have 1 million biomarker per person. Now 1 million is just so many. They're so super high correlated, we couldn't see anything. So you go into kind of representatives, you go into clustering, and you take cluster representatives, and that's called actually a target SNP in that literature. So we make a dimensionality reduction to 460, and the involved parameters are 1,380. So we actually have a bit less parameters than sample size, but the design matrix is still not full rank. So what we do in terms of model, nothing new. Just take a well-established model. It's a multivariate linear model. The new thing is just I have a multivariate response with 79 different y's, different responses. And I just want to find out the significant beta coefficients here. Okay? So here are my tests as before. And I want to adjust for multiple testing. And I'm actually going to look over many of these tests. In total, we're looking at more than 110,000 tests here. Okay, but we can do this. There is structure in the problem. I really think I should skip that. So what we do is we go hierarchically. There's an additional feature which we build in. That's very efficient. You should test hierarchically and not just blindly your 100,000 hypothesis. And if you do that, you get a couple of results. So here you see actually my 460 different biomarkers. These are cluster representatives. And for each of them, I see how many significant responses I have. I have 79 responses. And some of these biomarkers have a higher degree of association to these behavioral responses. So for example, I don't know, the guy 100 has maybe about 10 or 12 different significant associations to a behavioral response. So that seems to be an important biomarker. Kind of the vice versa question is more interesting in a way. So here on the x-axis, I plot my 79 different response variables, my behavioral task experiments. I have 79 experiments. And I ask the question, for example, is risk aversion, suppose risk aversion is number 40, does it have a high association to genetic biomarkers? And for example, this number 40 has most association to genetic biomarkers. Unfortunately, I'm not allowed to tell you what experiment 40 is. It's kind of still confidential, but think for you it could be risk aversion. Risk aversion is maybe most closely associated with genetic information. That's of course not true, it's a different experiment. But that's the sort of analysis you want to do. So here are rigorous p-values under some assumptions which allow to give you somehow a statement to quantify the significance between genetic biomarkers and behavioral task experiments. Conclusions. So I think I roughly have given you a maybe introduction into two different lines what you can do to quantify uncertainty. And maybe there are new methods coming out. There are really essentially no good methods so far. One of the methods is based on projection, and it's kind of mathematically very nice and clean in terms of it's optimal under some assumptions. You have good power, it's optimal under some assumptions, and I took two famous people which stand for optimality. Neyman Pearson lemma is kind of optimal power. So these kind of projection methods aim for that sort of thing, having optimal power, at least under some assumptions. Now on the other hand, you have these more sample splitting, subsampling methods. They're more reliable. They're more stable, but there is a price to be paid in terms of power. I think we need more theoretical and more empirical validation to understand which of these methods really work well and which are not. All methods are implemented in an R package, and this is maybe a good thing to end. Without conditions on the design matrix, you cannot assign strength or uncertainty of a variable in a high-dimensional setting. Now these conditions unfortunately are uncheckable. There is progress on this side where you have checkable conditions, but most of them are uncheckable. And given the necessity of such uncheckable design conditions, I think one has to be careful when these p-values come out as numbers. And my important final phrase is, I think you have to be careful, and confirmatory high-dimensional inference still is a challenge. Thank you.
So we have time for a few questions.
Okay, go ahead.
How do these methods compare to stability selection?
Okay, so stability selection is another way how you can address stability and quantify uncertainty. Stability selection mathematically only controls the expected number of false positives. It doesn't give you p-values. So it's a bit a different aim, a bit a different goal. If you're happy with expected number of false positives, stability selection is surprisingly good. So.
Well, given you also have this work on sparse graph selection, what you're saying is that somehow the the x's that you observe, even if they are small, you should be able to learn whether or not it's a sparse graph. I mean, did you make any connection to that work?
Not yet. I think, well, and I'm not sure whether I have the capacity to do this all, but I think the principle is exactly the same. So now this sparse graph estimation, undirected graphs, I think you're probably talking about this.
Exactly. Sparse decision-making.
Yeah. Then hopefully, I mean, under some sort of the analog of the beta min condition, you see too many edges, and you would get an estimated graph which contains the true graph. And now comes again the same principle. You would like to have p-values on these edges, and you can do this. I mean, we haven't done it rigorously, but you can apply the same methodology. For example, the inversion of this KKT formulation. This will lead you exactly to some sort of. I mean, one may be surprised if one does it carefully, but I don't see any problem why this shouldn't carry over. So I'm very confident that it would carry over. We have done it for GLMs, not for linear models, to generalized linear models, but I think undirected graph problem applies as well.
Yeah, if I understand correctly, you're assuming this restricted eigenvalue assumption on your design matrix X. Yeah. So in compressed sensing, where we have sort of RIP type conditions, we get to, well, in theory, we get to design our own matrix, and so we can hopefully get something that works. I mean, do you really believe that your design matrices are likely to have these properties?
No, that's of course great. I think that's in a way one of the most convincing applications in high-dimensional inference, I think in signal processing and so on, because you have control over your design. So then even if you're fine with RIP, then you're in business. I mean, my condition is weaker than RIP, so it's fine. So if RIP condition holds, all of this holds. My area of application is more in genomics, and there you have no control over the design. But absolutely.
Does that mean, maybe there'll be other tools like, I know Joel Trott has a result on deterministic matrices where you can show that you get recovery from random, if the sparse subset is randomly selected, then high probability you'll get it. But it's not a condition on the design matrix, it's a condition on the support, so you put the randomness on the support set. Would that be your appropriate model for this sort of statistical?
So the question is whether we could make a statement that with high probability that these conditions are still fulfilled, or?
Yes, so you get recovery, or you get some sort of statistical estimation based on with high probability on the support set rather than with high probability on or a particular property on the design.
Yeah. So that's of course true as well. You can get some results like this, that with high probability, for example, you can get the support, and then you're done. However, if you want to get the support, you need this beta min assumption. So there's no way. So suppose your beta j is 1 over square root n. You have no chance to detect that for sure. So in a 1 over square root n range, in the classical range, nobody can tell you which probability converging to 1 you can detect that variable. And you also will not, so that's the sort of setting and scenario where I'm interested in. So if the beta j's are small, I need to have something on top of it which gives me a clear answer whether it's sufficiently large or not. But once you have large coefficients, I think there are very clean results on support recovery. And then in that scenario, in a way, you don't need that machinery. It's just there or not. So.
Okay, one more maybe. I guess my question is on the example that you showed, that you identified different mutation or marker than what the biologists have identified as significant. Did I understand that right? Is that a red flag of the theory, or there's something that explains that maybe it's a proxy or something like that that the biologists have identified?
Are you talking about the behavioral economics example?
No.